In this video, I'm going to showcase to you what I like to do with everything, which is I have reverse engineered the Deepseek R1 model, and I put it back together again, and I can tell you exactly how it works and what they did and what the unique innovations are for the model itself. Before we do that, let's dive into the research paper that comes with the model, which is Deepseek R1 Incentivizing Reasoning Abilities in LLMs via Reinforcement Learning. And I'll distill this paper down for you. So let's go to here, and then first of all with the contributions. So the main two contributions that this model makes are post-training the large-scale reinforcement learning on the base model specifically. So they directly apply the reinforcement learning to the base model without relying on supervised fine-tuning or SFT as a preliminary step. So number one, this is all reinforcement learning based, and then we'll get into the method for the reinforcement learning in a second. But then secondarily, they utilize distillation. So they take and they train their bigger models and the big model, and then they distill that data down into the smaller models. And then that's how they train the small models in this instance, is just through pure distillation. So pure reinforcement learning at the top, pure distillation at the bottom. So they're cutting out a lot of the middleman essentially here, right? And then then they summarize their results, which show that it outclasses a 1 in a lot of instances, and then it's a really cool approach. And then what we care about here very specifically is their model for their reinforcement learning algorithm. And then essentially it is here. And then they use a GRPO or group relative policy optimization in order to train their model. This is fancy math, but this is essentially the algorithm that they utilize in order to make sure that the model is able to update its own policies, right? This is the training mechanism essentially for the model. And then on top of this, you have a unique reward mechanism. And then the unique reward mechanism that they utilize for this model is two rewards that they combine into one. They have an accuracy reward and a format reward. So accuracy reward is it rewards the model and it evaluates whether the response is correct. So very simplistic, right? The accuracy of it. And then the format reward. So in addition to the accuracy reward, the format reward rewards the model for following the format of thinking. And then so that within the code I'll show you, we put in these think tags. And then within this, within this paper, they point out kind of during the training an aha moment, right? So wait. That's an aha moment I can flag here, right? Where it's the model has through this training method, what ends up happening, this becomes an emergent property where the model thinks it's like, okay, I'm going through, I'm thinking, my response is wrong. My thinking is wrong. Wait, let me take a step back. And then let's reevaluate this step by step to identify if the correct sum can be, etc. And then that that let's take a step back is what ends up being emergent within this model and being very powerful within this model, right? And then so that's what they demonstrate within this overall. And then so here's the code for this. And then I'll say this up front, right? And before we dive into this, it was easy for me to build this out because I built out a similar model maybe about 2 months ago. GRPO has been big in research for about 2 months, right? It's like if you've been keeping an eye on research papers, you've known that this is the avenue to go towards, that it does cool things with the model, right? And so essentially how I look this up, I look at this very simplistically is it's a cool mechanism because you're essentially treating the model as both the student and the teacher, right? And then so I set it up a little bit differently than how they set it up here. I set it up and I wrapped it all in a Monte Carlo simulation, which is just like how I would do a typical reinforcement learning outside of a learning model, like an LLM. I thought I would make it more kind of like a video game, and then so I could see like what was going on and like how the model's doing and what's going on during this training process, right? And then so I take it a step further and I create a simulation, an actual simulation out of this via wrapping it in a Monte Carlo algorithm. And then within that, I explicitly instruct like the model that, you're a teacher, here's how the teacher operates, you're a student, here's how the student operates, and then the teacher is teaching the student. I give it a curriculum to operate off of. So I like the not find like the elimination of the SFT step in the beginning. I do that. Right. So this model does that where I don't do that, and I gave it my PFAP data. As kind of like its starting curriculum or that SFT and like that supervised fine tuning, and then I let the model run in my simulation, and I train a model, and I think it was like a Llama 3 model that I trained all of this on. I let it run, and I let it run for a few hours, and then within my simulation, as I let the model run, the model realizes that it's in a simulate that it's training, like which like isn't supposed to happen. Like the student asked the teacher, what's going on, like, and then the teacher responds that like it's simulating. It's simulating prompts via Monte Carlo algorithm, and like explicitly like tells the student exactly what's going on, and then the student just like stops responding, like it just doesn't output like valid responses for like 20 minutes. It just, I don't know what happens, and then it all of a sudden it produced outputs again, and then so I never touched this again post that, and then like it kind of scared me, just flat out honestly, like that going through that was like I can't explain like why certain things happened within that, but so it's cool, right? Like aha moments and things like that can come from this training. I can validate that you can get that from this type of training effect. So let's focus very specifically though on the Deepseek training, because they do a little bit differently than my training method, right? So let's dissect their full method. And then so the very first thing that I do is I define the model, and then so I create two models, right? The first one is I'm creating a small model, and I'm creating a hyperbolic model, and just using and utilizing hyperbolic space, and then so I have that here for my forward pass, and then I just pass it from hyperbolic space back to Euclidean space, just how I would build out this traditional neural network. In this instance, is essentially, to me, it will make it like, while this is a small model, it's going to outperform like other small models just because of this small little tweak that I put in here, which is why I do that overall, just explaining that out. And then I have here as well a smaller model on top of my small model that we're going to distill into. And then this is just a very small model, right? So like this is a small model, and then this is just an even smaller model. And that's just kind of the layout of the two models. So we're looking at two models here. And then two models, two reward functions. But the two reward functions get combined here, as you can see in the end, into a singular reward function. But so again, going back based off of the research paper, so we're computing both the accuracy and then a format reward. And then we combine both those, and then the model gets a combined reward. And then we train it for both accuracy and format, making sure that it's doing and training on both of those things. Then we define the training function itself, which is a pretty standard training function for so this is that GRPO, all of that math. This is what that math looks like, right? And then it's just with regards towards, so we have our standard forward pass, and then we're passing essentially in this instance the prompts, which I'll show down here, that we're passing to the model on the forward pass, and then we decode the responses, and then we compute rewards based off of the response, and then we are making sure that we have those tags in there, so those sync tags, and then we're just simulating it in this instance for demo purposes. We're simulating the decoding. So our model doesn't have a decoder, right? We're training an encoder in this instance, and it's important probably to highlight and to point this out in this instance that with most neural networks, it's split up into encoder and decoder, right? And then so in this instance, we're training the encoder and I'm simulating the decoder, just for simplicity's sake for you. I don't have a trained decoder that would be able to actually decode what we're doing here for this, and I don't want to train one, so I'm just simulating the decoding process flat out. And then then we have it do and compute the rewards based off of the response that it's given. So that's the back propagation, and then we feed that negative that reward and the feedback back over. So we do have that back propagation, and that's what like essentially creates our feedback loop and how the model is able to train itself. Right? If we didn't have back propagation within this step, we wouldn't be able to create this feedback loop of learning. And then so taking a step back here, so a lot of people knock where we're at right now with regards towards AI very specifically for this reason, right? Because it doesn't follow exactly human learning. And then to me, I take a step back from this, right? Like to me, I separate human learning from learning. This entire process, what we're doing here, this back propagation, feeding the rewards backwards over the network, etc., that part is taking it a step further than what actually occurs within the human brain. If I could remodel my brain to do that step, I would do it. Why not? But the human brain doesn't do this step. And then so for some reason, people knock that as a bad thing within these models. But to me, that's a good thing within these models, right? It's just showing like AI learning is not human learning, and the way that an AI manifold works is not necessarily the way that a human brain manifold works, which is not necessarily the way that an elephant brain manifold works, which is not nearly the same way that like an octopus elephant manifold works, right? Just very straightforward to me overall. Highlighting that before we dive deeper here. So then let's dive deeper. This covers essentially like the model training and the whole reward process overall for the model itself, right? And then we have that distillation function. So where we take essentially all of that training from the model, like what the model learns, and then what it's outputting and its outputs, and then and its weights, its final weights, and then we train that to the student model, right? So we just we create the prompt, extract the prompt, convert the prompt to embeddings. Then we have our teacher model, we get the output. Then we have our student model, and then we calculate the loss, mean square error between the teacher and the student model as far as the outputs. And then within our toy example here, I'm simulating some of this process here with regards towards the distillation process, but it's very straightforward, right? You're literally, I'm simulating the process of the teacher model, like teaching based off of the prompts, essentially. But we're just all we need to do at the end of the day is just extract the weights from the model with regards towards distillation. And what I want you to take away from this specifically is that like distillation, like student teacher learning within AI is like very straightforward, right? It's just this, like one function gets you what you need for distillation. And then so we just put that together into our main function, and then so our main function is just creating our neural network, and then so our both of our networks. So it's we have our input layer, our hidden dimension, and our output layer, and then this is for our small model, and then I'm using a Riemannian R atom as far as my optimizer. And then the data set. So I'm just using very dummy data and then 3 specific like prompts, right? So solve x plus 2 equals 5, and then the target in that instance would be that x equals 3. Second prompt, what is the capital of France? My target would be Paris. And then explain Pythagoras theorem. So my target would be that a squared plus b squared equals c squared for a right triangle. And I want it to say like exactly that. And then so I train the model based off of this, and then so I'm just training it for 10 epochs, and then I'm making sure that I'm truncating the responses as well as the input data, which like I already know what the input data will be there, which is totally fine to truncate in this instance. And then once I do the training, then I distill to the even smaller model, right? So then I just distill to my model here, and then I need to create an optimizer very specifically for the distillation, and then for the smaller model, and then so the smaller model will just be utilizing standard atom as opposed to R atom for the teacher model. And then 5 epochs as opposed to 10 epochs on the training, and then some same truncation of 50 characters for the max sequence length. And then going through, we train the teacher model, very straightforward on the prompts, and then again, so I'm simulating the response within this, but this is making sure that we would want the response in this format, right? So response think, simulated response, and then end think. So making sure that it's having those tags and those end tags, and then it would have multiple think tags within its response, right? And then within that, we get our loss rate and our combined reward. And then we would want to make sure that our loss is actually like going down in this instance. Since I'm utilizing in summer and simulating data in this instance, the loss rate goes up as we go up here, because it's like what's going on, and then it like somehow finds like something to train on in this instance and goes down a little bit and is like, actually maybe it wasn't, and then it like it trains on something, right? Like it finds some pattern within this data, because our loss rate goes down ever so slightly within this. We can see like a 0.0329 loss rate, which is more than zero. So it picked up on something. I don't know what it trained on. And then we have our distillation process, and then so we distill to the student model, and then we have our distilled student model, which you can see that the loss rate of the distilled student model is incredible compared to the loss rate of the teacher model, right? Like very small loss rate. So essentially, everything that the teacher model learns, and then so in this instance, it's like a lot of that simulated data, it passes all of that on to the student model, right? So this student model is a lot smaller, but it like everything that the teacher knows with regards towards this, the student just knows automatically. Like the student is an expert in this, which is amazing for this distillation process and how it works, right? Like I can take this very large model, this huge model, distill its outputs, and then train this very tiny model very specifically on those outputs. And as long as we stay within this output range, so like solve x plus 2 equals 5, if it was like x plus 3 equals 5, x plus 1 equals 5, we stayed within like a very close range within that, this model is going to like outperform anything as far as a baseline model that we could ever throw at it. And it would outperform even larger models when it comes to like these specific performance classes and these specific instances, right? Like, and then so like when you see a lot of like papers that come out and they're like, this beats O1 in this specific class, they're using distillation oftentimes in that instance in order to get those results, which is why I oftentimes poo-poo on those results, right? Because it's like, this is like if you're looking to game benchmarks, this is an easy way to just game benchmarks via like distillation, and you can do it, and you can do magic things to your benchmarks just through distillation alone, and make it your benchmarks seem cooler than they are, right? Like you can, I mean, it's like I don't like it. I like you can take literally anything. I don't see any reason why literally you shouldn't. Just pointing it out. Like if you know that you're going to be trained on a benchmark on something, train a model and then distill a model and then pass your trained model to your distilled model, and then do your distilled model on the benchmark every single time, because it's gonna outclass your teacher model, the pre-distilled model, like 10x, and then so you're just gonna like game the benchmarks essentially, like for whatever task you want, right? As long as you're distilling like around the benchmark, like what you're benchmarking around, like you're good to go, bro. Like do that, and it like no one will know, and it will be good. Just highlighting that, like that's exists within these like. And these reasons and highlighting these things out are a lot of the reasons why I don't like support putting in large language models for corporations and things like that, right? Like there's so much of this that you can game with regards towards just the research purposes. And then so when you put financial incentives around it, it makes it a lot easier to game. And then so I like to not have those financial incentives around these areas for myself, so that I can be the one to highlight and point these things out for you from a non-biased perspective. And then so if you like that, and if you like this type of content, please like and subscribe. Thank you very much.